Hello, welcome everyone to the second day of Wasm in Web3 Talks. And we discuss the experiences of WebAssembly implementations in Web3 and on the blockchains to better understand the challenges, opportunities, and requirements for modern Web3 architecture, exploring dev toolchains and workflows for coding, debugging, and deploying executable code. Let me briefly remind you the format of the event. There are 3 talks today, and after each talk, we have Q&A part. So please be active and remember there are no obvious or stupid questions. We all are here to share learnings and resources between the projects. And the last session we have for today is a chill music set by DJ Fuzzy Logic. Pew, pew, pew. So we've got an invite. You've got an invite to your email in Hopin, and there is a link in chats everywhere. If something is not clear, please ask me in chat or email. And I want to remind you also about POAPs badges that you can still claim. Also sending the email to anna@fluence.one, and you'll get your badge proof of attendance of this event. And now let's welcome the first speaker, Mike Voronov, R&D engineer at Fluence Labs. And Fluence is a Web3 protocol, framework, and tooling to develop and host applications, interfaces, and backends on permissionless peer-to-peer networks. So Mike, please take it away.
Hi guys, thank you, Anna. I'm glad to be here for a second time. And today I'm going to tell you about how we are using WebAssembly at Fluence. In particular, the agenda of my talk is as follows. So first of all, I will tell you a bit about Fluence, what we are doing and how. And then we are talk a lot about what is Marine runtime, how it looks internally, and explore some tools around Marine. Marine is our general purpose runtime that is based on interface types and the model linking. And also it exposes sharedness and linking scheme, possibility to link modules. And as the last section, we will cover a bit, the last topic that is about our intermediate representation called AIR and about Aqua VM, our virtual machine that interprets this AIR and that located inside Marine on our network. And let's start with Fluence overview. And Fluence is a so-called open application platform. In turn, open application platform is a thing that consists of three main other things. First one, as usual, Web3 project, it is P2P. It's completely decentralized. And this P2P nature allows Fluence to compose different APIs, different services, data, processes inside network, and so on. It could be said that from the developer point of view, Fluence is about composing. It's about composing everything. We could compose modules in the service and the services with help of our new language into some so-called super service. And second two things here is about marketplace, is about monetization. We believe that in future, Fluence network will allow developers to get paid automatically by the fact that their code are used by anyone in Fluence network. The second important things here is Aqua. Aqua is our programming language that inspired by P-calculus and especially by process calculus. And this language allows to program network requests across our network. It's designed to coordinate and orchestrate network calls without any central gateway. So all peers inside our network are peers. There are no any leaders. They play the same role. They could host services. They could be relay and so on. So they completely decentralized. And Aqua is interprets and is interpreted by every service at once. The third important thing here is services. Services could be considered as usual as general microservices. They first of all WebAssembly based, and that's why they're sandboxed by design. I will show you later on a dedicated slide that a developer could set settings for each module inside services. It could have different constraints, different abilities, and they could play different role inside service. On the slide, you could see a model of Fluence network that consists of 3 peers and 2 clients. Clients usually browsers. And Aqua Aqua allows a user to compose these services located inside peers and compose their through WebAssembly interface types. Each service could be either stateful or stateless. They could access hard drive through WASI. They could also call some external services through spatial gateway functions. We will also cover their later. And here you can see on the right side that one service could interact with 3 other different services that are in orange boxes. Here you can see IPFS, some unknown microservice, for example, databases like MariaDB, MongoDB, Oracle, and so on. And this like microservice written on WebAssembly allow you to interact with some, I don't know, well-known services that can't be, for example, compiled to WebAssembly. And it's the power of Fluence and power of composing. And let's dig into Marine runtime in details. Actually, you could see my previous talks, and where Marine was called FC. We have changed name about several months ago. So please, when you see Marine, when you see FC in our code base or in the slides, please like notice us and think about it is about Marine. And from the service-oriented view, Fluence could be considered as in a following scheme. Here you can see that we have several modules form a service. Here are modules as the usual WebAssembly modules that compiled with our SDK, and they link together and form one service. And in turn, several services could form a so-called super service or backend. And it's important that these services could be located somewhere in network. It doesn't matter where. They could be on one peer, they could be on different peers, it doesn't matter. With help of Aqua, there could be composed to some super service. And for users, this super service could expose functions. And they are like, they're transparent for users. And also it could be seen as a function as a service. But it's a bit more, of course, than just usual function as a service. And as I said, Fluence service is just a group of modules that link together with help of shared nothing linking scheme. And as you know, shared nothing, so actually there are 2 types of linking. The first one is shared nothing, the second one is shared everything. And the difference here is what module exposed to external world. For example, to a host runtime or to other modules. In shared nothing linking scheme, there are only exports and imports that are visible for different modules, for other modules, except this one. And in shared everything, module could expose everything. Yes, for example, constants, globals, tables, memory, and so on. Marine currently support only shared nothing linking scheme, and the scheme actually could be implemented only with help of interface types. So under the hood, we are using WebAssembly. We are using Wasmer as a base runtime, and Wasmer crate that was highly modified by us, called interface types. And with help of that, it's possible to make such a scheme where, for example, you have a service that consists of 3 modules. One like facades, it's one that just exposes API of all services. And second one, for example, could be some database like SQLite. We have SQLite that ported to WebAssembly, also like in such a way that is compatible with other modules and with interface types wrapping in our Marine. And the third one, for example, could be some authentication module. Yes, it doesn't matter why. An important thing here is that they linked by linking corresponding imports with corresponding exports, as shown on the scheme. So like each module encapsulates all state inside. So no other modules could access to some memory data and so on. And we have three types of modules. The first one that I already mentioned is facade. This facade module, they expose API of all modules in service, and only there could be only one facade module in service. In config, the last one, and only these modules could be called from Aqua scripts. No other modules are like all other modules are inaccessible for Aqua scripts. Second one is pure modules. They can't access file systems. They can't call external binaries. They just should contain pure logic. And the last one is effector. Effector through WASI could access file system, could call external binaries, and some other stuff. So the difference here is that pure modules could be safely loaded into each service, into each runtime that located somewhere on user machine, and they're completely safe. And effector modules, they could access file system, but they could access only with constraints, with some settings. And let's show how it's look like. Here you can see service configuration. Each service has a configuration file. It's based on a TOML format config. And here you can see that this example of so-called Euro download service. It's the simplest one. It consists of three modules. The last one is already set is facade. It should be set as the last one in config. And here you can see that there are no other special settings. Second one is a curl adapter. This one is different from facade because it has mounted binary sections. And the sections allows this adapter to call external binary through CLI interface, through standard operation system CLI interface. For example, this module could call curl that located with through this path on the operation system. The last one is local storage. Remember that this is a simple example, just it's intended to show possibilities of linking. There are no any logic to split this into three modules. There, we could see on examples that they're rather simple. There contains about 20 lines of code, but that's just example. And here you can see that there are a bunch of additional settings. For example, for this module for local storage, we could enable special logger. I will not cover this logger because it's not so interesting, and you will find it well described in documentation. Next setting is setting about count of memory pages that can be used by this service. These pages are WebAssembly pages of 64 kilobytes, and we could set this setting for each module. So we could set maximum amount of memory that module could use inside Marine and inside the operation system. And also the last setting here is WASI. With WASI, we could set which files and which directories are accessible, could be accessible from this module. For example, here there is this directory site that located somewhere near the binary of module, and also we could map it to we could make aliases for this directory to access this through aliases, but not through a whole name. Okay, and from general perspective, Marine could be presented like in this slide. Here you can see that in Marine, we could load several services at once, and they could consist of separated modules. There are not any interdependence between them. They're just each module belong to only one service. And here you can see also that through WASI, effector modules could access to operation system, call external binaries, and so on. Marine has so-called layered architecture. We have 3 layers to feed different purposes. On the third layer, so that layer that contains app service and Aquamarine VM, this layer intended to run services. That's aim of app service, and to run Aqua virtual machine. That's aim of Aquamarine VM. But actually, Marine, the second and the first layer, could be used in another different scenarios. I think that's probably most important one and most useful here is the so-called entity component system pattern that widely used in games and in scenarios when you need some plugin system inside your other system. So I believe that Marine could be easily integrated to other projects and used as a used to allow a CE pattern. And on the first level of engine, we have a lot of APIs. Here you can see only important ones. For example, you could load module with some module config. In module config, there are some settings that we covered on previous slides, and one that dedicated to host closures. I will cover it later. Also, you, of course, could unload module by name. And while module loaded, you could call it by name, call by function name, and with arguments. Here, please note that there is iValue. There are no in arguments. There are no any row types. iValue is enum. I will show you later what fields it consists of. And also, you could expose state of WASI state of module and module interface. Here, by interface, I mean interface of modules, exports functions that module expose that could be called from a module. And second layer that also could be used not only by us, they intended to provide several variants of constructors. They also provide several functions to work with configs. And it has a function that mimics for call, but receives arguments not in this form, but in form of JSON. So you could just call it with JSON arguments and get also JSON arguments. And also it defines several host imports that's special for network. And iValue that I mentioned previously looks like this. Here you can see that iValue consists of general Rust types. Yes, it's here you can see some primitive types, strings, vector of bytes, vector of different types, and records. And host closures that I also mentioned looks like this. So here, this one is intended to code closures that could be called from a module. It could be called from module imports. In many projects that I have seen that based on different runtimes, Wasmer, Wasm time, and so on, host closures were based on row types. So you should manage your own by your hands, yes, how arguments will be passed from Wasm to host and so and in different direction. Here you can see that this mechanism provides you a way to abstract over it and work on with iValue. So there are no any row types. Of course, you could access to memory with this context. It's Wasmer context, but in many almost all situations, it's isn't needed here. And on the slide, you can see how import for mounted binary, that like option mounted binary that each module could be extended, works. So here, functions that return this host import descriptor, and inside it there is a like closure body. This closure body receives arguments and receives context that isn't used inside this closure, actually. And here there is a special function that implements calling mounted binary. It doesn't important, just the usual Rust function. And here you can see that so the results here actually it's just a Rust structure. And like we have special function called to interface value that wraps this result into I value. And like this return result. And the whole function returns this host import descriptor that consists of some additional fields, like this host, this host closure, this body that I covered previously. Argument type should also be specified, yes, because it's dynamic linking that's supported by Wasmer. But like to link it properly, we need to know types that closure should receive to allow, for example, type checking, and also the same for output type. And if there is some problem, for example, in lowering or lifting types between raw WebAssembly types and some non-simple Rust types like string, vectors, and so on, there is special error handler that looks like this. It's also closure that allow you to do some, I don't know, some recovery after error or print some error message or something like that. And the whole import looks like this. Here, please also notice that there are any things related to raw arguments. We work with I values, and we receive I values and we return I values. There are no any issues with reading memories, writing memories, and so on. Okay, let's cover the next topic that dedicated to Marine SDK and tools around. Hello world for Marine runtime looks like this. It's similar to Wasm mentioned and to other different projects. Here, please note that there are no any traits that you should implement it. There is only that differs from like vanilla Rust function. Here is only this procedure macro. So this macro means that
recording in progress.
That this function greeting will be exposed and will it became expert from this module. And here just a hello world. Yes, it's I know 6 lines of code, and it allows you to code on vanilla Rust with some limitations, of course, because Marine macro, for example, doesn't support traits, generics, and like stuff like box or C and so on. But this will be added in future. Like previously, I covered where download the service and showed config for it. And here, let's see how it looks like from a code perspective. Because here, remember that it consists of 3 services. They're just really simple ones and contains 20 lines of code. And how it looks from a code perspective. It's this function is function from facade module. This function allow you to download some some bytes from URL with curl, and then save it in the file. And these 2 functions, download and file put, they're from different modules. And to allow this module to use it, yes, there is this known Rust FFI mechanism that here is also used And the only thing that you need to add is also marine macro here, marine procedure macro. And also specify from which module this function should be called. And here also link name is also works. For example, this function that in this module called file put, actually it imports with name put from module called local storage. And like curl and local storage modules looks like this. Like in real example, it's a bit longer. You can find it's this by this link. But here is the main logic, and here you can see that this download function actually will call this function without any additional work. It just work with Marine. Also, more complex example, of course, supported. For example, here you can see that records could be used, and records could be also contains fields that in its store other records. And also we support passing by reference in imports and exports. But please note that since it's a shared nested linking scheme, memory is copying, and the passing like in exports by reference is like a syntactic sugar. It doesn't allow you prevent copying, additional copying. Okay, and here I want to cover something special. Actually, it's special because I haven't seen such possibility in other projects. This is how we approach in testing. So to allow users to test their code in the same way as it could be loaded in Marine, we introduce a new macro called Marine test. And here you can see how it works. Here also our whole world that contains only one function, greeting, and imagine that we want to test it. And to test it, we write test as usual, we wrap it with KUG test and so on. And here, except just test that we should write in vanilla Rust, here we need to write Marine test. And in attributes, we should specify path to config file and path to modules. Yes, folders that contains all modules of the service. And we also should specify an arguments like this one. This is all code that should be generated by this macro. And inside it, we could operate with export functions from this module. It's different. This code won't be compiled to WebAssembly and code. It works a bit different. Here, new Marine instance will be created. This Marine instance will load all modules from this dir, and according to this config, and all modules from this one will be supported from Wasm. So here we test not a native target, we test a Wasm. So by calling this greeting, actually we call Marine, and in Marine we call functions that compile to WebAssembly. This allows users to make comprehensive tests for service that contains several modules, because you could access different modules. Modules should be specified in the arguments of function, and only this module could be accessible inside this function itself. And this approach is very flexible. Also, we are working now, and this new version will be ready in 1-2 weeks. This version of Marine test allows you to test several services at once. We could specify services as a previous one, but with specifying their names, like here. And also we could interact with services and each module that each service contains. Here you can see example for where service one is called, especially this facade module that provides function code process data, is called from service 1, and the result of this code is then passed to process data of service 2. And with this result, we could do something, for example, compare it with some, I don't know, expected value or something like that. So here scheme is different from other projects because here, except this, again, this function like isn't compiled to WebAssembly and then run. This function is run as native, but all calls of this function, they actually call WebAssembly code, compiled to WebAssembly. And these tests allow you to test services as more close to how it will look like inside real runtime as possible. Let's cover like last topic of this section, how the module multi-module calls work internally. Also remember our example with 3 modules of real downloader service. And actually for each function that imports or either export, there is a dedicated interpreter. This interpreter is that interpret interface types instructions. For example, here we have seen 3 modules, and for each module there will be different Wasmer instance. Yes, for facade, curl, and local storage. And for each export and for each import in this instance, there will be corresponding adapter import and adapter export. And imagine that we could call, we want to call function curl from a module curl. And to call this function, there is a bunch of code of interface types code that should be executed. So at first, there will be executed these 4 instructions. They are intended to lift string. Remember that curl has curl receive string and produce string. It's 1 argument and 1 output value. And this code is intended to lift string from memory of curl module and then call curl adapter, this one. Next step, there will be like these instructions. These instructions are intended to lower string into a memory of curl module. Yes, here you can see, for example, function that lower memory. Actually, these instructions do like first they allocate memory of string size that passed from this adapter from the left side. Then it called lower memory that copies string from a host memory to a curl memory, this module memory. Finally, like real function from an instance will be called. It's like after lowering, yes, we could use row types, and with row types we could call row Wasm function. And the last step here is to pass result string back to the facade module. Here we like in export adapters, the only thing that we need to do is just to lift memory back, lift string, and then we should lower it back, should lower it to a facade memory. So that's how interface types works. It should be noted here that we're using now the first version, so-called first version of interface types, because the interface types proposal was completely changed about a year ago, and now like we are waiting when it became stable to use the second version of interface types. But currently, the first version is work. We added several instructions. For example, you can see here DAP and swap2. There were no such instruction in the specification, but it's impossible to implement such a scheme without them. Also, we did some work to optimize the scheme to like specialize some, I don't know, some instruction to allow them work better than it was initially written, and so on. So it's just work, actually. So regarding tools, like we have tools. The first one is called Marine, and it's in aims to compile modules. It works as a Wasm pack or other tools that, for example, as a Wasm engine, that uses two stages compilation scheme. Marine is also exposed as such a scheme, but I think it's not so interesting. More interesting here is REPL. This tool is intended to test services by hand. Yes, here you can see that services called IPFS loaded inside REPL, and here it contains two functions: IPFS pure. Two modules: IPFS pure and IPFS effector. And we call the first one with JSON serialized arguments. That is actually an array with 3 numbers, and this is put this code internally through CLI interface. It's called IPFS put. So it's like store inside IPFS network this piece of data. And by using hash that provided by this function, here we could get back our 3 numbers. Yes, and you can see that their number is the same. Okay, how fast is it? With SQLite, we also supported Redis. Redis is also accessible in our network. You could use it as a building block of services. And here you can see some numbers. For example, Redis instantiation takes about half a second. And by instantiation here means, first of all, compiling from WebAssembly to native, and some work to instantiate import exports, interpreters for exports, and so on. So function call, usual function call, here you could see that takes 67 it's microseconds. The first call takes a bit more, about 3 milliseconds, because we have some lazy linking inside, and all next calls will be faster. Okay, let's cover our last topic that dedicated to air in our Aqua virtual machine. As I said, we introduced a new language called Aqua, and here you can see a simple example, of simple code written on Aqua. The full code could be found by this link at the bottom of the slide, and here you can see an application called Fluent Path. That's collaborative editing, and this function handles user joining. Here you can see that this function receives one argument, user, and returns join results that have this structure. And this function is the same. It goes to peer that identified by app user list peer ID, and on this peer it calls service called user list that identified by this service ID, this one. And on this service, function join is called with argument user. And the result of this calling is returned from the whole function. So that's how you could transmit through Aqua and with operator on. You could transmit execution flow to peer that identified by this peer ID. It's pretty easy. Of course, I won't cover the whole topic about Aqua. You could find a lot of documentation and a lot of videos on our channel. But Aqua, why I mention it? Because Aqua actually compiled to our intermediate representation called Aquamarine intermediate representation, AIR. As a compiler here written on Scala, and it just compiles. This AIR then interprets by our interpreter. This interpreter written in Rust, and it's then compiled to WebAssembly, and then it could be loaded inside Marine runtime. So here you can see like our complex scheme where code written on Aqua compiled to air, and then it could be launched on our interpreter that's in its turn loaded into Marine. But it's for user, there are a bunch of tools that allow to automate all of this. And also with, again, like here this interpreter is loaded into Marine. And Marine runtime are allowed only to launch into nodes, not in the browser. But also this interpreter, exactly the same, works in the browser with browser runtime, and also it could be loaded into Node.js, exactly in the same way. And this interpreter works in such a way that it interprets about 10 instructions, as they're like inspired by process calculus and p-calculus. They just allow you to program how network requests will be moved across your network. And from a formal point of view, this Aqua virtual machine is a pure function that takes two data, previous one and the so-called current data. This current data is data that comes from a network, and previous data should be stored into a node that manages such interpreter. And the result of this is a new data and a list of peers where this new data should be sent. And this function actually is like state transition function. It's just some form of like finite state machine. It's a pure function. There are no any imports here, and that's why it's really easy to run it on a browser or Node.js and something like this. It allows also host like Node or browser works in a synchronous way. Because there are no any blocking calls here. It just interprets instructions and provides like some form of commands that host should be should follow. Okay, here you can see another picture. It's how like our network could be represented. There are two layers. The first layer is the execution layer that is handled by Marine. And into this, and we have peers that could load several services, and also with services, Aqua virtual machine is also loaded. And in turn, these peers could be composed by Aqua. That's also another way how to present yourself Fluence network. It consists of several nodes, again, peers, and we have several dedicated peers called clients that usually like browsers. Each like peer here runs Aqua virtual machine on nodes that not browser. They run it through Marine, and on the browser they run through browser runtimes like V8 or SpiderMonkey. And from a Marine point of view, interpreter is just a module, just a service that consists of one module, but with special host closure. This host closure is something special because it allows interpreter to call different services, because services itself can't call other services. They could communicate only through modules that form the service. Okay, and today, I presented you several things that we use WebAssembly in Fluence. I covered Marine virtual machine. You could find it by this link. Our SDK and tools. You could find this by Rust SDK link, Air, Aqua. And if you're interested in our project and if you want to follow updates, please join to our Twitter, subscribe to our Twitter. And if you have any questions, like if you, for example, watching this in the record, you have any questions, so please ask me by this email or by this Telegram nick or through issues or somewhere. So we're very open for any questions, for any proposals. So please, I know, find us and ask them. Thank you very much. I would be glad to hear there. So hope you enjoyed.
Thank you, Mike. Yes, we truly did enjoy. Thank you for the talk. Looking at the questions, we don't have questions so far. I actually think you're right that most of the people will watch our streams in record. So those who are watching, please just send your questions if you have. Okay, so thank you again, and let's move on to the next speaker. We might have a little break, like a couple of minutes, so stay tuned. So next one we have Syrus Akbary. He's a mathematician with deep expertise in open source development, and Syrus is the founder of Wasmer, an open source runtime for executing WebAssembly on the server. And he will share how Wasmer improves Web3 apps. Okay, let's have a little break, few minutes, take some water, and let's get back in.
Hello everyone, I'm Syrus, and today we are chatting about WebAssembly in Web3. And basically, it's going to be a story tale on how Wasmer can help your ecosystem, especially if you are on the decentralized platform Web3 world. So, presentation about myself. I'm Syrus. I'm the founder and CEO of Wasmer. If you don't know what Wasmer is, we are a server-side WebAssembly runtime that basically allows anyone from companies to enterprises to blockchain applications, basically to anyone, leveraging on WebAssembly to run any kind of software anywhere in the cloud, in the edge, in blockchains. And you can find reference to myself and to the company in almost all the slides. So my email is syrus@wasmer.io, or Twitter is wasmer.io, and our GitHub is also wasmer.io. So that's a bit about myself. I'm from Spain, so that's why I have an accent. But yeah, I was gonna say that feel free to ask questions, but I think this is only one way. So I'm not sure if I'm gonna be able to see your questions. So let's start. The agenda for today. Today we are going to see why WebAssembly is important, especially for Web3. What are the challenges that you usually face, especially if you're trying to execute WebAssembly on blockchains? How Wasmer can help on those? And one of the things where I wanted to put more emphasis today is what is the state of the art right now regarding the ecosystem, and what the future entails. What are the next things that are coming in the Web3 WebAssembly world? So as probably most of you know, WebAssembly is emerging as the universal engine for smart contracts. There are right now multiple engines, especially on WebAssembly, that make that possible. And I'm gonna overview why WebAssembly is key for the Web3 world, for decentralized applications, blockchains, and so on. First is because it's a universal format that can run code universally. That means running code in any chipset, in ARC64 or ARM, in Intel chipsets, in RISC-V when the future comes, or any operating system, in Linux, Windows, iOS, Android, it doesn't matter. Also, one of the main advantages of WebAssembly is it can be fully sandboxed. And I'm saying it can be because it depends on you, but by default, it's secure by default. So unless we create system calls that are insecure, WebAssembly and the WebAssembly runtime will be fully secure. And one of the main advantages that we have on WebAssembly is because it is a very light abstraction on top of chipset instructions. It's really, really fast to run. So we get almost to native speeds, usually with a slowdown of 5 to 10%, and sometimes even with a speed up. So what are the challenges when running WebAssembly in Web3? These are things that probably you already know if you are using or executing WebAssembly on your blockchain, which is you can have JIT bombs. And what is a JIT bomb? A JIT bomb is a program that takes longer to compile than it takes to execute. And basically, with this, you can have a malicious actor that tries to get your blockchain down by sending you code that is gonna have a very big complexity when compiling. So basically, it might have O(n) square or n cube timings when compiling the module, and we don't want that. Also, one of the challenges that we have when trying to run WebAssembly across a heterogeneous infrastructure is that we want deterministic execution. So that means if I'm trying to execute a module that does operations on nonce, nonce are not a number, so kind of infinity or so on. So when we are doing operations over these numbers, or yeah, basically WebAssembly doesn't assure deterministic execution across chipsets, and usually what we want is deterministic execution. So that's one of the biggest challenges, and that's why in some runtimes usually they disable floats, which are what usually introduce non-deterministic behavior. Another challenge that you might have when running WebAssembly server side is that you want to scale as much as possible your WebAssembly modules, so you can run as many smart contracts as possible within your chain. So these are the main challenges when using WebAssembly in Web3. So now I'm going to be presenting Wasmer. Here is the marketing or my biased approach or recommendation, which is Wasmer is really an ideal runtime to execute WebAssembly on decentralized platforms. Why is it good for your ecosystem? First one is because we have a compiler that allows you to compile WebAssembly code in a way that is completely linear. So that means that like no matter if your module like weighs 1 megabyte or 10, it's always going to compile at the same speed, which is usually like 5 megabits per second. Obviously, like depends on your mileage and how powerful your chip is. But like the compilation is fully linear. That means that like you are not going to see O(n) squared complexity when compiling, which usually means that you're going to get into compiling certain kind of programs much faster than other optimizing compilers, such as CraneLeaf or LLVM. On one side, I have to say CraneLeaf is not really like an optimizing compiler, or at least is not at the level of LLVM. But we have seen some cases where CraneLeaf, for example, takes 1 minute to compile, and single pass takes just a few seconds. So in general, like usually you want a compiler and a runtime that is not prone to JIT bumps, and for that, Wasmer is really good. The other thing that we have is deterministic execution across chipsets and platforms. So that means that when you run a WebAssembly module in Windows, it's going to run exactly the same way. It's going to give you exactly the same input, same output for the same input. So this is quite important, and we have like a lot of tests assuring that. And one of the things that we have been like very focused on since the beginning is to have the platform to be fully highly scalable. So on that front, yeah, we have optimized a lot. The startup time is just a few microseconds. And we offer the developer and the company or the blockchain like different alternatives to play with to ensure that you get the maximum performance. So let's continue with who's using Wasmer. So we got Near Protocol, Cosm, Wasm, and Space Mesh. These one are, I want to kind of like highlight those, especially because they are sponsors of the open source project. They are collaborating with a sponsorship to make sure that like the Wasmer evolve at a healthy place, and also to make sure that we have features that they may need. But apart from that, from them, there are tons of other blockchains that are very using us. To put some examples here, we have Fluence Labs, Holochain, ChainSafe, Elrond, Parity, which are just like trialing Wasmer, and the Band protocol. So these are some of the blockchain ecosystems that are using us, but not all. Actually, like I discover a lot of new ones each week, and more or less like this one are the most well-known ones. So what we did with the sponsorships, I'm here trying to attract you to collaborate into the ecosystem if you believe that like WebAssembly is a key part of your infrastructure on the decentralized world. So we optimize for startup speed. We lower it from a few milliseconds to just some microseconds. So that was a high improvement. We optimize for really fast completion times. So in the case of single pass, we did like a 4x improvement on the speed when compiling. Of course, if you use parallel processes or threads. And one of the things that we did lately is making Wasmer fully usable in the browser. So what this means, if you have a Rust program that is using Wasmer under the hood, before you were only able to use your Rust program in native executables. Basically, like you compile your program natively, you try to execute it, and then like basically Wasmer runs under the hood. One of the nicest things that we did in Wasmer 2.1, which is not yet released, but it will very soon, is that we allow your Rust program to compile to WebAssembly through Wasm bindgen without any syntax change. So you can, when using Wasmer in your Rust program, you can target the web or you can target the server. It really doesn't matter. And this is quite big, especially for what we believe is gonna make users use Wasmer in a lot of new places. So what is coming next regarding Wasmer, the runtime? First is, thanks to the sponsorship of Custom Wasm, we have been working on full ARM support. We are still on the way on developing this one, but yeah, we are getting very interesting results right now, and we'll say we are 30–40% on there. Other thing that I'm super happy to announce is that as of today, we just merged support for single pass in Windows. I'm not sure if Aviv from SpaceMS knows this yet or not, but basically we added full support for single pass, and that means that when using single pass in Windows, you can basically you can execute Wasmer with single pass, which is awesome. Other thing that actually Near protocol has been working with is on adding signal-less support. This support right now is quite experimental, and we have not merged it yet, but it's on the way of basically making it work and trying to get the findings. Also, we want to have very easy, usable, and pluggable WebAssembly modules from different languages, which means we want to add support for interface types, and we are actively working on this. Also, we are working on a new cross-chipset architecture, which is basically refactoring single pass to make it much more scalable across different architectures. So let's look into the cool things. What is the state of the art? Where are we at right now? And this is not regarding Wasmer, but regarding WebAssembly. What are the different cool things that are happening on the ecosystem? First one, let's talk about the SDKs. I've been watching what Fluence is with their framework, which I forgot their name. And it's not very different from what Definity, for example, is doing on Candid. So basically what I'm gonna say is probably that applies the same for the framework that Fluence Labs has been working on. So with Definity Candid, which I think is a very original approach, it allows you to create universal SDKs that can run on Definity Internet Computer. This is basically more or less a precursor to interface types, which allows you to create universal APIs that can run in any language. I just remember what was the name of the framework from Fluence, which was Marine. So Definity Candid, I think, is very similar to Marine. But there is one thing that I think is very interesting about Candid, which is formally verified, which I think is quite important, especially for blockchain or decentralized applications, and also is uniqueable, hashable. So I would recommend you to take a look on the project. They have support for multiple bindings, and I think it's just the beginning. Probably this is gonna feed back into what interface types is gonna become. But Candid is a pretty good approach, and probably the one from Fluence as well, although I didn't have as much time to review it. Yep. I think I deleted the wrong slide. So in here, I was supposed to talk about the compiler, and I remember. So I'm just bear with me about what I'm gonna say. So we have discovered a very novel approach for compiling WebAssembly code back to machine code in a way that is super fast. So right now, with single pass, we are generating the code at runtime, and we are detecting what are all the different WebAssembly operations, and we are generating the machine code related to these WebAssembly operations at runtime. This is great, but we can get much better when generating the code at runtime, and as well to generate code that is more or less optimized. So by using a novel approach that relies on the LLVM compiler, we can get LLVM to do that ahead of time for us for each of the WebAssembly operations. So then the compiler only needs to patch the location of the addresses, and that's it. I'm sorry about the slides. I will upload them later, and it will have this slide fixed. So one of the things that I remain super excited is what's going to happen in the future. Not just like where are we at right now, but what are the interesting paths that we will see in the future. So here are some of the ones that I remain most excited about. First one is universal smart contracts. I think that thanks to interface types, we can allow developers to create smart contracts in any language. So basically like Marine with Fluence, Definity with Candid, and interface types in general are going to be really key to create universal SDKs that allows us to run smart contracts cross-chain. This, of course, will depend on the blockchains to decide on common SDKs that can be usable. But I think there is a very good and potential opportunity for almost all the chains to agree on a API that is going to be universal across smart contracts. I think this might take some time, but I remain very excited about this one, especially because when you create a smart contract, you might be able to execute in one chain or the other. Other feature that I remain very excited about is pause and resume. So what this means is being able to pause our virtual machine as it's run with the WebAssembly module and restore it anytime after. So why this might become important? As a smart contract get more powerful and we can do more things with them, we might need to execute the smart contracts that are becoming more and more complex. So for example, in the case of Definity Computer, they are starting to allow, I believe, like some Wasm modules, but basically like you are gonna get more contracts that are more complex and complex over time. And it might become very interesting to be able to pause a smart contract, perhaps like when a node becomes like very overbooked, and being able to translate or to move that execution towards other node. Or perhaps just kind of like being able to recover state from a partially executed contract because something happened on the node. So I think this feature is super, super exciting. We are looking forward to support it at Wasmer, and I think it's going to help a lot on the blockchain ecosystem as well, or Web3 ecosystem. And here is one of the future things that I think are going to happen that I really remain super excited about, which is IPFS. So I'm going to do a demo, not a demo that I have created, but I'm going to do a demo in a few minutes on like what this thing commenting. But basically like the main thing that this slide is trying to entail is that we can use IPFS as the distributed file system for both distributing the contracts or the applications that we want to execute, and also to distribute the storage that this application might use. So sometimes applications like such as Rust applications, they might not require any like file system, but if we try to run like more complex examples, like let's say Python relies in a lot of like files or system files that are actually required to be able to run the runtime successfully. And leveraging IPFS to be able to run this module across basically like anywhere, I think is super, super interesting. So in a few minutes, we are going to see an example of how, for example, run a decentralized Wikipedia search. And this is going to be executed in the browser, but it's going to showcase like what are the different opportunities on the space. So bear with me. I'm going to try to share my whole screen in a second, and let's see if I get it right. Awesome. So I'm going to share my screen again, but I'm going to share other screen. So here we are. Probably you're seeing my browser. You will like what I'm going to demonstrate is a full text search on Wikipedia, and that means kind of like a very large database, like gigabytes of database. And in here we are going to try to execute search on this data set, which is super, super large. So let's try to search for Wasmer. I'm just curious how, like, what's going to happen. Cool. So it's funny. Not sure what are all these different articles, but we can see that like Wasmer got searched in a lot of appeared in a lot of like different articles. Let's actually like search for WebAssembly here. So we can see that like we were able to execute the logic in my computer, but the storage is somewhere else. So let's inspect about like what is happening here underneath it. I'm gonna search again so you can see the requests. Let's reload. Yeah. So basically, like what is happening here is locally, the module is requesting kind of like the very big data set. And usually like what happens when you search on databases is you don't get the whole database in memory. Usually like you search at the beginning the indices, the index to see like where certain words might appear. And then based on different indexes, you do like you seek that file to get into that specific content. So you say there might be an index saying like, oh, this word appears in this offset, in this other offset, and this other offset, and then basically like you search on all of them, you get more indices, and then like you kind of like the engine merge them together. So in this case, there has been like 28 requests that like come when we try to search for Horace Slughorn, and this is basically like what it's doing is retrieving the storage from somewhere else, but it's executing locally. So this is one of the examples that I think is going to become very key. For example, to have like search on IPFS on the Wikipedia, but not just that, but also to be able to run like, for example, Python, but where the file system is completely distributed. So that's one of the examples that I'm most excited about. And this is so far kind of like as far as we can get on the presentation. I'm gonna jump into the last slide. I'm not sure if it's worth for me to share or not, but I'm gonna do it. So yeah, just basically like that was the presentation. It's a little bit shorter than the rest. I wanted to keep it lean, short, and basically focus more on what are the exciting things that I think are gonna happen in the future. So having said that, does anyone have any questions?
Thank you, Syrus. That was a great talk, and people in the chat also thank you for the talk and saying a full ARM support in Wasmer. Yeah. I don't see right now the questions. I'm sure they will come up as we see now and from yesterday. Maybe we should give people some time to just come up with questions. So just watch the chat in Hopin and the stream on YouTube. So there might be some questions coming up. Yeah, thank you. Okay, congrats. Really excited about a lot of the developments that are coming. Comments nice. From Hopin, from Andre. Okay.
Awesome to hear. Thank you for inviting me to speak here.
Thank you so much, Syrus. That was a great overview of the ecosystem and updates that are coming. Let's move on to the next speaker. And awesome. The next speaker we have, see you, thank you. The next one we have Steven Allen. He's an engineer from Protocol Labs and building such well-known projects as IPFS, libp2p, and interplanetary linked data. And Steven will share about operating on IPLD data in Wasm. We will have a little break. We are waiting for Steven to wake up and join. So stay with us. It's not going to be a big break, but you will see. I'll send a message to the chat when we are back. Thank you, everyone. And if you have any questions, please send it to the chats anywhere in Telegram, in Hopin, in YouTube. We are everywhere. Thank you. Okay, let's get back in a while. So hi everyone, welcome back to Wasm in Web3 Talks Day 2. We have the last but not least speaker for today. And also after the last talk, please join us for the DJ set by DJ Fuzzy Logic. We will have some chilled music in Zoom for an hour or so, and just relaxed networking. So I'll introduce again Steven. Steven Allen is an engineer from Protocol Labs, and he's building such a well-known project as IPFS, P2P, and interplanetary linked data. And Steven will share about operating on IPLD data in Wasm. Steven, please take it away.
Hello, hope you can hear me. I'm currently working on trying to mash up IPLD, which is the Interplanetary Linked Data System, and Wasm. Basically, IPLD is a system for, I guess it's an abstraction over Merkle trees, over Merkle linked data. That basically allows you to work with multiple different types of Merkle linked data, like Git or Ethereum or Bitcoin blocks, or even just arbitrary tags of JSON. You can link together by a hash in a standard way. So we use this to have standard transports that operate over, where they can transfer and sync Merkle trees between multiple computers. We also use this to write with selectors over data, where you can actually query the data with standard language. We also have languages for we also have languages for describing different data structures and the types and types you can have there, that kind of stuff. Okay, so that's what IPLD is. The core things you need to know is that there are CIDs or content IDs, and there are codecs. The codec is a format like Git or JSON or whatever. Could you go to the next slide? That was actually what I was describing. I was bored earlier. But yeah, you have it there. Next slide, please. So what we're trying to do here is basically mash up again IPLD and Wasm. So instead of just working over just links and stuff like that, which you usually in Wasm, it's the function types that you have. Instead, you operate over IPLD data. So it's actually give you structured types. But it's cool because it actually lets you sort of link to an entire tree of data, which is not something that you can otherwise easily do. And basically, you take your function to take an input CID, which is a content ID, and you have an output CID, or an output DAG. if you want to have like a method or define a method, you would take in an input state and an input parameters as, again, effectively objects, and then you spit out a new state and a new output. So for example, we're planning on using this to define a virtual machine for PowerPoint, at least that's the hope. Yeah, we're also planning on having EVM support. Yeah, can you actually hear me? Or is it? I can
yeah,
try
we hear,
it's
but there is
noisy.
some like beeping sound on the background, and it's
Yeah,
really
let me just
difficult
quickly
to...
walk down the street. I'm really sorry.
No worries. That's a
yeah, let me just
digital
walk
nomad
away.
life. We know it.
Yeah, sorry, I thought this was going to be live.
Okay, show us some of the views of the city.
Okay, so hopefully it's a little bit better. Let me go keep on running. Okay, hopefully that's a bit better now. The way
Yes.
the construction. Okay, again, I'm really sorry about this. Yeah, so basically, yeah, like our goal is to build something basically a VM on top of this, but our goal is also to be able to use this for like IPFS in general. So like we have this problem in IPFS where like we have to like you kind of have to bake everything into the protocol, where instead we really have to be able to ship code to people. So our goal is to be able to basically ship Wasm modules as IPLD objects, as IPLD trees, and transfer them with content or message addressing, and then kind of define things later. That's not entirely the point of this talk. It's just one of those. Next slide, please. Yeah, so this is trying to cover like why we want to do this. Again, what I'm talking about here is like with IPLD data, it's all network transparent because everything is always serialized. It's a bit of a problem as well, but it means like you can have these functions and like your methods, and, like at every point you always have the serialized data. You can always transfer between nodes. It's also reasonably efficient in certain cases where, for example, because like you can link to other objects, only the change data needs to be transferred. So like you can point to a very large tree of things. Same with Ethereum, you can point to like your state tree. You only need to actually like move around the changed pieces. The other cool thing is like if you have proper support in your VM, you could lazily load code. So for example, I can have a module that links to another module by CID, and then it can lazily load the code on demand as necessary. Finally, yeah, you can pass around large data structures without copying. So whatever hopes here is like, I can have my smart contract can call someone else's smart contract and like pass in some sub DAG of the state, have that smart contract operate on that sub DAG of the state, and then return like the transform DAG. The EVM kind of supports this right now where like I can call someone with a delegate call, but then I give them full access to everything, or I can send them data and then receive the data back. But then like I have to like pay for sending everything. But in this case, I can kind of say, look, here's a reference to all of my data. Do what you want to it. I can get it back, then I can verify they did it correctly, and then link it back in. Yeah, it's secure because everything is content addressed by CID. Everything is also structured, unlike unstructured data like it's just arbitrary bytes. So you can actually explore the data, understand it, and there's a bunch of comment to all. That's really why. Next slide, please. The why not is inefficiencies. Everything is always serialized and always hashed. The impact of this depends on the granularity of functions. If you have like tiny little functions, it's not going to work. If you have just sort of like big things like kind of like little contracts, it works better. But this can also be optimized away in many cases. So the hope really is that we'll be able to find ways to do that. But yeah, that is really what I wanted to talk about. Okay. Anything else?
That was it for the slides that you sent. That was the last slide was fifth slide. Why not? Okay, yep. that was it.
That was it. Yeah, it was just introducing the
okay.
Yeah, and again, I really apologize. I thought I was going to give this presentation live at 7 o'clock, and this was just going to be like a meetup and like talking to people. I should have read things more carefully. I'm sorry about that.
No worries. We all know we are all running in between the meetings and working a lot. So
actually, okay. I have questions. Was the presentation understandable at all? If not, I'm not going to be like pissed it off at all if like we just drop it. So I just want to make sure that it's actually understandable.
Well, we will have another session with Andres Rosberg at least. So maybe we should do around 2 or actually version 3 of this event if people will be up for it, and we can do it like more in a quiet room to record your talk, for example. But we have a question for you from Peter. Will it also calculate the new state in the parameters are if the params are the same?
I mean, it depends on your system. So like one of the cool things about this is that in a blockchain, yes, you're gonna have to probably just always execute the same thing. Offline though, you can do a lot of memoization because like your code will be linked to by CID, your parameters will be linked by CID. So as long as you like have kind of like that, you can describe that as a single object, then you can just cache all the results and just not have to redo anything. But again, it depends on your system. So actually, I can give an example here where this is really cool. For example, you can do like type resolution in the system itself, and you can cache the outputs of that type resolution by basically like calling type resolution functions that are defined in Wasm. And they say like, oh, well, my inputs are the same and my code is the same as it was before. I'm just going to use my cached results.
Okay. Thank you. Thank you for the answer. I hope that was, yeah, Peter says thank you. Yeah, good. So Stephen, thank you so much again for today, for finding the time in between your work and working on your projects to share with us your experiences and insights. And
yeah,
hopefully see you again at the other workshops and conferences. Okay, so next we will have, that was the last but not least session. And I want to thank everyone again, all the speakers who joined us during these 2 days, all the organizing team. Thank you, Aviv from Space Mesh. We were doing it together. Thanks, OneCakes for also helping us with covering the costs. Thank you, Fluence Labs. I'm from Fluence Labs, so they were helping me a lot in all the organizing and everything what we are doing here. And let's move on to the DJ session by Aviv, by DJ Fuzzy Logic. And yesterday that was really cool. We had a nice chilled evening, or for someone it was morning or daytime, depends on your time zone. We've been watched from all over the world, and more than 250, actually almost 300 participants joined this conference during these 2 days. And I'm sure that people will watch the recordings and will have questions and will have discussions. So let's continue all of our community vibes and community collaborations. I hope that we will get more and more fruitful projects talking to each other, and developers joining the conversation about WebAssembly in Web3, in blockchain. Thank you, everyone. And please join Zoom. We will share links again. And yeah, hope everyone has a good day. Bye, everyone.